Okay, so let me go ahead and start. So last two lectures we've been going over some op-amp circuits, right? And op-amps are one of those really quite versatile and incredible building blocks that we can use for doing quite a bit as far as dealing with analog voltages and analog signals. Now, that being said, there's some more that I want to do, but I think we should take a quick break in the op amps in order to address analog versus digital and kind of see how we can jump back and forth between the two. Okay, so if we're talking about digital signals, I just have one wire, let's say, for 1 bit. Now, that 1 bit can carry some information. It's either going to be a 0 or it's going to be a 1. And this is great if we want to use multiple wires to represent multiple bits in order to be able to hold and move data. However, what we've been dealing with in this whole class is analog. So let's say for the digital, our 0 refers to 0 volts and our 1 or logic high refers to 5 volts. But when it comes to analog, we have a kind of a disconnect between the digital and the analog, because with one wire, we can represent any voltage. And so let's say not only are we representing a logic 0 or 0 volts or a logic 1 at 5 volts, but we can represent 0, 0.1, 0.2, 1 volt, 2 volt, 3 volt, all the way up to, let's say, 5 volts. Now, when it comes to digital, we're talking about the world of the discrete. But when you're talking analog, you're now talking about the continuous world. And when you're dealing with analog, which at the end of the day, everything reverts to analog, even your digital circuits. As you've seen with your digital circuits, when you're constructing, say, an inverter, a buffer, you are essentially using analog components to do that. So you're abstracting the analog world in order to represent digital information, and that comes with a whole lot of benefits, and it's the whole reason we have computers. But at the end of the day, everything that we deal with is still with the analog world. So if you want to interface with the real world, you have to deal with the analog. So if you're talking about, any type of input or output to a computer system, it is analog. Always. So if you're talking about, inputs into a computer, microphone, this goes into your sound card. Well, what is your microphone? It's going to be an analog voltage. And what about your speaker coming out of it? Again, it's an analog voltage. Your inputs, even though you're pushing on buttons and it eventually turns into digital, you're still dealing with an analog voltage. And practically every single input is going to be an analog voltage at some point. So we need to be able to cross this boundary somehow. We need to be able to jump back and forth. Now, every type of sensor or input or output that you're going to deal with is going to end up being analog. And in the case of sound, your microphone, that's a transducer. Now, transducer is just a fancy word for sensor. So you're really dealing with a bunch of sensors. And so what we want to be able to do is come up with a way to jump back and forth between these two. We want to be able to take input into our computer from the analog world. So on one side, you may have an analog voltage, 0 volts to, say, 5 volts. And then on the other side, you're going to get digital out of it. However many bits you have. Right? So we might have 0, 0.1 volts, 0.2 volts, 1 volt, 3 volt, 5 volts, whatever the voltage is over here, and we want to be able to convert that into a number, be able to convert that into a discrete value. So what we're really talking about is converting from the continuous domain to the discrete domain. And so if you're talking about like something like your sound card, your microphone's producing an analog voltage, you're getting out digital values, and then you can store those values to memory and you can record speech or record anything. But also we want to be able to jump in the other direction, because many times we have outputs that are analog as well. So we'd like to also be able to take the digital domain which is coming in the form of several wires, each one holding a 1 or a 0. And we want to be able to convert that to an analog voltage. Say 0 volts to 5 volts. And you can kind of think of this as like your speaker, right? That's an output coming from digital, and it's got to get converted back to analog in order to come out of your speakers. And I'm using the sound card a lot because that's probably the easiest example, where on one side, say you have a microphone, and you want to record it, so you're saving digital values. On the other hand, you want to play that audio back. And so we want to be able to convert those digital values in memory, coming in the form of several wires, each representing a 1 or a 0, and convert that to an analog voltage, 0 to 5 volts, let's say. Okay, now a lot of the op-amp circuits we're going to be working with, really the goal is to adjust these voltages for the sake of getting them into a digital system. If you think about an amplifier, we've been dealing with amplifiers for a while now. Well, your microphone doesn't put out 0 to 5 volts. It puts out a much smaller voltage, 0 to 0.1 volt, 0 to 0.2 volts. And then that has to get amplified before it can even get converted into the digital domain. So what we're dealing with, and a lot of the stuff we've been learning about thus far, falls under the category of signal conditioning. So a very typical system that you'd be dealing with, whether it's embedded systems, FPGAs, or just computer hardware in general, you're dealing a lot with, we have an analog input, it goes into some type of signal conditioning. This might be amplification. We got to make the voltage larger. Maybe there's some unwanted frequencies we want to get rid of, so there's also an element of filtering in here. And yes, we haven't learned or talked about filters yet. But generally speaking, signal conditioning, amplification, filtering, or adjusting of voltages somehow. Maybe all of our analog input is negative and we want to make it positive. So I'd refer to this as scaling and offset. We need to take our -1 to -2 volts and move it into the positive voltage range. Depending on whatever analog signal we're dealing with over here, this would be coming from some kind of transducer. And so you can think of this over here as it could be a temperature sensor. It could be some sort of light detection. It could be some type of electromagnetic radiation, something like an antenna. Or it could be as simple as a switch. Or an adjustable potentiometer. You want to be able to raise your volume up or down. So you want to be able to measure some rotary change that a user has in an input. So maybe like a potentiometer, an adjustable resistance. Whatever the source is, 99.9% of the time, you're going to have to perform some signal conditioning on it. We're going to have to adjust the scaling and offset, maybe filter out some frequencies, some unwanted noise from it, and more than likely amplify it. Either amplify or attenuate, make the voltages smaller or make the voltages larger. And we do this before we even get this into a computational device, say an FPGA or embedded system. So over here, we'd have to go ahead and convert this from the analog domain to the digital. Now, once we go ahead and take our analog voltage, which is coming in as 0 volts, say, to 5 volts, then we get to turn this into a bunch of ones and zeros. Again, we're back at converting from the continuous analog domain into the discrete digital domain. So for the sake of recognizing the importance and value in the op-amp circuits we're going to be looking at, we really should kind of have an idea of how we get these signals in and how do we get these signals out of a computer. Because anytime we're getting something in or out of a computer, we got to deal with this conversion from the continuous to the discrete. Okay, and now this means we have two similar devices, but a bit different from each other in order to perform this function. We have DACs and we have ADCs. Okay, a DAC stands for digital to analog converter. And an ADC stands for an analog to digital converter. And if we're talking about a digital to analog converter, you're converting a bunch of ones and zeros into an analog voltage. So 0 or 5 volts, 0 or 5 volts, 0 or 5 volts, 0 to 5 volts, 0 to 5 volts, all on one wire. Because this can be 0, it could be 1, it could be 2, it could be 3, 4, 5 volts, or anything in between. But each one of these wires can only be a logic low or a logic high. And kind of the opposite function, if you think about the data direction going in this way, your analog to digital converter converts an analog voltage into a digital value. So you go ahead and you feed it some voltage on the continuous range of, say, 0 to 5 volts. And what you get out of it is a bunch of wires where each wire holds 0 or 5 volts. Okay, so we have two devices in order to bridge this gap between the analog continuous domain and the discrete digital domain. Okay, and what we're going to talk about first is the digital to analog converter, because it is similar, and also because the analog to digital converter uses a digital to analog converter inside of this. So fundamentally, a digital to analog converter is a simpler device, and we will analyze this first. Once we learn how to perform a digital to analog conversion, then we can see how we can use a digital to analog conversion inside of this ADC in order to convert from an analog voltage into a digital discrete set of values. Okay, so let's go ahead, let's zoom in on this and see how we can convert a bunch of zeros and ones into a voltage on the range of 0 to 5 volts, 1 volt, 1.3 volt, 1.4 volts, etc. Okay, and if you want a little bit of a practical example, this is your sound card audio output. This is what you're feeding your speaker with. So we are talking about the hardware that converts what's stored in memory, digital values, into an analog voltage that you use to drive the speakers on the output from your PC. Okay, so let's focus in on the digital to analog converter, or as we just generally call it, a DAC. And our DAC produces an analog value, say 0 to 5 volts, and it takes in a number of bits. And let's say we have 8 wires going in. 1, 2, 3, 4. I'm going to have to 5, 6, 7, 8. Okay, I should have made my box a little larger. And so each one of these bits is either 0 volts or 5 volts. But we have a least significant bit all the way up to the most significant bit. And now the number of bits that it takes in refers to the resolution of the digital to analog converter. So over here, this is not just a digital to analog converter, it is an 8-bit digital to analog converter. And so this refers to our resolution. In general, we refer to that as just the N bit. I could have a 4-bit digital to analog converter. I could have a 5-bit. I could have an 11-bit, 16-bit. And we'll see the benefits of having more bits in order to represent this 0 to 5 volts on the output. But in general, it's a bit easier and cleaner to write it out this way. We have some n-bit DAC that takes in an n-bit number of wires coming into this thing. And so more generally speaking, we would write it like this. Now, let's go ahead and clear up a couple of things over here. First off, we went ahead and talked about resolution. How many bits do I have? 4, 5, 6, 10, 16. Let me move my head out of the way there. So resolution, how many bits do we have in order to represent the voltages on or between the range of 0 volts to Vref? So over here, I need to know what my range of voltages out from my digital to analog converter is. Now, generally speaking, 0 volts to Vref. Vref may be 5 volts, and in fact, in all my examples, I'll use 5 volts as my Vref. So this could be 0 volts to 5 volts. So when we're talking resolution, it determines how many individual steps we have in between 0 to 5 volts. You'll see this in a bit. So resolution, the more resolution we have, the more analog values we can represent on this range of from 0 volts to Vref. And Vref defines the max analog voltage out that we can get from our digital to analog converter. And like I said, usually it's going to be taken from 0 volts. There's no reason I can't construct a digital to analog converter that gives me a voltage out from 1 to 6 volts. But generally speaking, we always have a ground in our circuit, so we might as well consider that the starting point. So, for example, Vref, if Vref equals 5 volts, then the range of V out equals 0 volts to 5 volts. And like I said, I'll be using that for my examples. Okay, so this is what we want to construct. Now let's go ahead and let's go with a low resolution digital to analog converter, because it's going to make things easier to write. So let's give ourselves a 4-bit DAC. Now, if it's 4 bits, that means we have 4 wires coming into this guy. And this means that D in D3, D2, D1, D0, where D3 is our most significant bit and D0 is our least significant bit. And coming out of this, we'll go ahead and let's say our Vref is equal to 5 volts. That means V out is going to be equal to 0 to 5 volts. And I'll write continuous just under here in order to emphasize that it's all values in between 0 to 5 volts. Now, with only 4 bits of resolution, we are limited on the amount of values that we can represent between 0 to 5 volts. So let's say with 4 bits, we can only represent voltages on the range 0 to 5 volts with 2 to the 4 or 16 discrete values. So in other words, this 0 to 5 volts, I can't infinitely represent any voltage between it. I can only break this range 0 to 5 volts into 16 different values. Now we refer to this as the step size. The step size is the smallest change that can be produced. Another way of thinking of the step size is it is the voltage that is referred to by the least significant bit. So I can say that LSB produces a voltage change equal to the step size. Now, you calculate the step size, as Vref divided by 2 to the n, where n is the number of bits of your digital to analog converter. And this is the change in voltage that is produced by one least significant bit, or change in one LSB. So for our 4-bit digital to analog converter, the step size is equal to 5 volts divided by 2 to the 4, which is 16. Or in other words, 0.3125 volts. So I only have the granularity in a 4-bit DAC in order to produce voltages that are a multiple of 0.3125. Or in other words, a change of one least significant bit produces a change in voltage of our output by 0.3125 volts. Now, we can always calculate the converted value. We can always calculate what the output should be for a given set of inputs by multiplying the step size by the numeric value of our n-bit input. V out equals step size times D in. Okay? So if we're given a numerical input of 1 or 2, you take 2 and you multiply it by the step size. And that makes sense because the step size refers to the smallest change or the change of that least significant bit. So if my least significant bit is 1 and all other ones are zeros, well, go figure. My output should be 0.3125 volts. But let's go ahead and let's set up a table for a 4-bit digital to analog converter and see what those values should be on the output. I think that'll kind of put this whole picture together. So once I've specified how many bits of input my DAC has and what my VREF is, I have an entirely defined digital to analog converter and I know everything that I need to know about it. I can calculate everything from here. So let's go ahead and let's set up this table. And let's give ourselves a few values here. Let's say 0, 0, 0, 0, 0, 0, 0, 1. I'm not going to set up an entire truth table for this. Now, this is all in binary, but the value for each one of these is 0, base 10, 1, base 10, 2, base 10, 8, base 10, 14, base 10, and 15, base 10. Okay. And then we want to know what V out is equal to for each one of these inputs. Well, all we have to do is multiply the value by the step size. We already calculated what the step size was. The step size was 0.3125. So in the case of what the value of all zeros on our digital inputs would get converted to on V out, all we have to do is 0 times our step size of 0.3125 volts. Well, what does that equal? Of course, 0 times anything is going to give us a V out of 0 volts. Okay, what about the case of when that least significant bit gets flipped and it is now a logic level high, or 1 volt? I shouldn't say 1. Logic level high, true, or we can say 5 volts if we're assuming 5 volt digital logic. Well, then it's going to be the numeric value 1 times our step size, 0.3125 volts. And that's going to equal, of course, 0.3125. Same thing goes for if we place the value 2 on our digital inputs to the digital to analog converter. What is V out going to be equal to? Well, it's going to be 2 times our step size, 0.3125 volts. And that's going to be equal to 0.625 volts. Now, of course, all values in between, but I did pick 8 because it's right there at the nice halfway mark. Well, if we give it a digital value of 8 on its input, it's going to be 8 times the step size of 0.3125 volts, and that's going to be equal to 2.5 volts. Now, 2.5 volts is right smack in that range of what we wanted as an output for our analog voltage range. Okay, so again, we're feeding it in digital values, and we're getting out an analog voltage on the range of what was dictated by Vref. Okay, if we get up there to the larger values that we could feed in for a 4-bit, the highest that we could give would be a value of 15 or F hex. But one below that, let's go ahead and do 14. 14 times our step size is going to be equal to 4.375 volts. And for our largest voltage that we could get out of this is going to be 15 times 0.3125 volts. And now this should be the largest voltage that we get out of this. And I'm going to go ahead and do this calculation. 15 times 0.3125. It's 4.68. It is not 5 volts. Okay, so even though our max on our voltage range we went with 5 volts, you can see that our largest value that we feed into it would actually be 4.6875. Or it could be 5 volts. And granted, that's a pretty large difference. However, it depends on the implementation of the digital to analog converter, what our full scale output voltage is. So we would refer to this as our full scale output. And there's a little bit of gray area over here. Is it 4.6875? But it should be 5 volts. Our Vref is 5 volts. That's the highest output that we should get out of this. Now, again, it depends on the implementation of your digital to analog converter. I'm going to cover in this class 2 different versions of this digital to analog converter. So I'm going to cover what's referred to as a binary weighted averaging digital to analog converter, as well as an R2R ladder digital to analog converter. We'll see those we'll see those in a minute. Okay, and you'll see the difference between this kind of last output over here, how it affects that. Okay, but for all practical purposes, the straightforward way, if you're working with an unknown digital to analog converter, is just calculate what the step size is, take your VREF divided by 2 to the power of your number of bits that you have, so 2 to the n, and that gives you your step size, and multiply it by whatever your input is, and that's your output voltage for that digital to analog converter. Now, we did that with a 4-bit digital to analog converter. However, if we increase the resolution, if we increase the number of bits, then we make the step size smaller and we increase the granularity of the individual analog values that we could output from the DAC. So higher resolution gives us a smaller step size. Or in other words, a change of one least significant bit produces a smaller change of V out. Or higher resolution equals more precision. So if you went back to the late 80s and you purchased a computer in the late 80s, you probably would be pretty proud if you had some 8-bit sound coming off of it. Or if you've played a Nintendo, you had 8-bit sound. Except when you listen to the audio coming off of your desktop PC or your cell phone, it sounds a whole lot better than your Nintendo did back in the early 90s. And a reason for that is because your digital to analog converter had a higher resolution, and so it had a smaller granularity to those changes that one least significant bit would produce, and so you could get better audio coming out of it. But let's go ahead and let's look at resolution versus step size. And for the step size, I'm going to assume a VREF equal to 5 volts, but keep in mind your range might actually be 0 to 3.3 volts or 0 to 10 volts. It's whatever you want. Or it's determined by the system that you're working with. So let's go ahead and let's put some different resolution digital to analog converters listed here. Let's say we got a 3-bit, a 4-bit, an 8-bit, a 10-bit, a 12-bit, and a 16-bit. And if you're really fancy, maybe you have a 24-bit digital to analog converter. Okay, the number of steps for each one of these. Well, if we have 3-bit, the number of steps that we could have is 2 to the 3 or 8. The number of steps that we would have for a 4-bit digital analog converter, as we already calculated, was 16. For 8, it's 256. For 10-bit, it's 1024. For 12-bit, oh, this is getting nice, 4096. And if you have a 16-bit digital to analog converter, you have 65,536 discrete values that you can use to represent your range of 0 to 5 volts. This is a lot of resolution. Okay, the step size. And remember that this is the smallest change that would be produced by changing that one least significant bit. Well, it would be for a 3-bit, it would be 5 volts divided by 8, or 0.625. For a 16-bit, it would be 0.3125. That's the one that we're using for our example. For an 8-bit, you get 5 volts divided by 256 discrete values. 8-bit's not bad. The smallest change that you could affect for V out would be 19.53 millivolts. For 10-bit, I'm just going to go ahead and write it. It would be 4.88 millivolts, 1.2 millivolts, and over here at 16-bit, 0.076 millivolts. Once you're in the microvolt range, it's hard to start getting higher resolution than that. You start running into issues where your components and their tolerances start to create problems for you. But nevertheless, you can see that you can have the smallest change on the range of 0 to 5 volts with a 16-bit digital analog converter is 0.076 millivolts, or 76 microvolts. That's a very small voltage change. Now, we are going to cover two different designs of digital to analog converters. The first one's going to be the binary weighted resistor. And the second one, which tends to be a little more preferred, is the R2R ladder. Now, each one of these has strengths and weaknesses to these two different designs for digital to analog converters. And I think overall the R2R ladder ends up winning for a few practical reasons. But let's go ahead and let's cover the binary weighted resistor first. I just lost my papers. Sorry, I have papers overflowing on my desk right now. Let me pause. For a binary weighted resistor DAC, the idea is pretty simple. We're going to take each one of our digital inputs and we're going to use a one resistor for each digital value, and we're going to use and change the resistance in order to weight that one bit of information. So for our least significant bit, we're going to give it a value of R. Now for our next most significant bit, we're going to go ahead and give it a value of 2R. And so forth. Notice I'm going to be using powers of 2 for the values of these resistances. So R, 2R, 4R, and 8R. And our V out is the weighted sum of all of our voltages. Now, I'm writing VB0 because this is going to be either 0 volts or 5 volts, but I want to emphasize that this is a voltage, not just a digital value. If it was just a digital value, I'd say B0. B1, B2. But because I want to specifically say that the voltage is what's present on this wire, I'm denoting that with a large V. So each one of these is 5 volts or 0 volts. So I could give this a value. I could make R equal to 1K, at which point I'd have 1K, 2K, 4K, and 8K. Now, in order to calculate what V out is equal to, we have 4 voltages and we have 4 resistors in series. So I should say a resistor in series with each one of our voltage sources, and then we have the weighted sum on the output. To calculate this, we're going to have to use Millman's theorem. But first, I think I'd like to share an LT Spice example so that we can see how the output changes for all of our binary inputs in terms of voltages. So let me go ahead, before I go through the derivation for what V out is equal to, let's see what the output would be in an LT Spice model. Now over here I actually have 2 different DACs that I've created. But let's focus on this binary weighted DAC. And what I'm going to do is let's delete this one. Oh, that's not what I wanted. Delete this and delete this one. Okay, so let me go ahead and kind of step through what I have set up here. Okay, so first off, what do I have down here? Well, I have 4 flip-flops. And I have these flip-flops set up as a counter. So I'm just starting at 0, 0, 0, 0, and then I feed in a clock signal, and then this starts counting up for a 4-bit value. And I have my outputs as B0, B1, B2, B3. And so if we go ahead and look at the output from this counter, this 4-bit counter, in order to stimulate my 4-bit digital analog converter, then let's go and look at the waveform over here. Okay, so as you can see, my least significant bit, bit 0, and you can see over here, VB0 is down here. I start off at 0, and then it goes up to 1, and then it goes back down to 0, and it goes back up to, well, when I say 1, I mean 5 volts for logic level 1 or logic level high, but it goes up to 5 volts, 0 volts, 5 volts, 0 volts, 5 volts, etc. And then my bit 1, my next most significant, or my next least significant bit, stays at 0 and then goes up to 1, and then so forth. So you can see that my 4 bits here are counting up. So in this space, I have an input of 0. In this space, I have an input of 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 15, my max value that I could have for the input to a digital to analog converter, for a 4-bit, that is. Okay, so that's what my counter is doing. Now I'm taking the output of my counter and I'm feeding it into my my binary weighted digital to analog converter over here. So I have B0, and actually I had this backwards when I wrote this out. Let me fix that. And so now you can see I have an 8K for my bit 0, a 4K for my bit 1, a 2K for my bit 2, and a 1K for my bit 3. And if we look at the output, my output, I'm calling it VDAC from my binary weighted digital analog converter. If I switch back over to my waveform over here, you can see my output. Let me delete this pane. Let me add one, and for there we go. And you can see that for my output of all zeros, I get 0 volts on the output. For an input of 1, I get a value of, let me take the measurement here, 333 millivolts. For an input of 2, I have 667 millivolts, and so forth. You can see when I have an input of 8, I get 2.66, which is what I would expect, about half of my VREF. And all the way up to my max value of 4.99 volts. So you can see in this case, my max, my full scale value is actually 5 volts on my output. Okay, now that's just a byproduct of this type of digital to analog converter design. Okay, but you can easily see the 16 voltages that we can produce given our 4-bit input.